I'm recording. Okay. All right. What's going on? So I'm trying to solve this problem. Oh yeah. So there's a contest. 205th weekly Leetcode contest, and so like I was able to figure out 3 problems during the contest, and actually I had like 30 minutes remaining. So um, pretty much I had enough time to solve the hard problem, but I didn't figure it out. But I'm gonna solve it right now. Um, Solving these 3 problems it's pretty good. Okay, so this remove max number of edges to keep graph fully traversable. Okay, so I've already read the problem, so I already have an idea of where I'm going to start. So the main idea is that what I didn't really recognize is that this is a problem where you could like use a disjoint set. Sorry, disjoint set. So yeah, so disjoint set is an idea for is a methodology for using. It's like saying, let's say for Alice and Alice, we want 1, 2, 3, 4 to all be contained in one set, all connected to each other. There might be other ways to solve this too, maybe with like Tarjan's algorithm. I don't know if it has anything to do with those algorithms. But yeah, so first idea is, can you use a disjoint set on this? Um, and I really don't know. I'm not 100% certain how you can use a disjoint set on it, but what I'm thinking is um, what am I saying? So I know this is a disjoint set problem, and I think you can use 2 different disjoint sets: a disjoint set for Alice and a disjoint set for Bob. And at the end, you want to return if those disjoint sets um, are equal. No, dang it. Now that more I think about this problem, I don't think I really know how to solve it. Um, yeah, I'm missing some type of like key insight. So I'm pretty confident, I'm fairly confident that maybe this one set will work. Maybe also, I heard something about a sort and greedy algorithm. Um, yeah, I don't want to waste time on this question anymore. I've already thought about it quite a bit, so I'm gonna look at the solution and solve it. Like it seems like something I should learn. Yeah, because right now the only hints I have is that DSU will probably work. I think I believe a DSU would work, and also some type of like greedy sort maybe, perhaps. No, that's for a different problem. But yeah, some type of DSU would work. Um, I just need to figure out. Um, I guess I just need to figure out what edges are extra. I mean, I'm thinking if you do use a union set, what's gonna happen? You know, like let's analyze this straightforward. So let's say we have 2 disjoint sets. We have one for Alice, we have one for Bob. So I'm just talking through this. So you have one for Alice, you have one for Bob, and I'll start with Alice. So we look at the first edge. We look at 1 and 2, right? So for 1 and 2, can Alice traverse from 1 and 2? And I say yeah. And okay, now I check if they're already union. If they're not union, union them. So now for Alice, I have a disjoint set 1, 2, and then for Bob, or not, I'm not gonna worry about Bob. And I go to the, well, I guess I'll worry for Bob too. So can Bob also traverse 1, 2? Yeah, so I have him in a disjoint set. And then I go to the next edge. Next edge is this one, 2 to 3. And since type 3 anyone can traverse it, I say, okay, well, have 2 and 3 been union? No, they haven't, so I union them together, and I do it for both of them. Then I go to the next one. The next one is 1 and 3. And this is type 1, so I think only Alice can traverse it. Then I ask, is 1 and 3 in the same set? Yeah, so since they're connected, that means we already know that Alice can traverse um, between 1 and 3. So yeah, we don't need it, right? So we don't need it, so we just say delete that one from Alice. Um, and also we delete it from Bob. Okay, cool. And then we go to the next one, and the next one we go to 1, 2, and 4, and they're not connected. This is a 1, so I think this means connected for Alice. So we're going to connect 4 into this disjoint set for Alice. Then we go to 1, 1, 2. So 1, 2 is mapping 1 to 2. Um, oh my bad, for 1 to 3, by the way. Yeah, so 1 to 2. So 1 to 2 is for only Alice. It's already there for Alice, so I'm going to say, oh, delete that one too. And then, so I'm basically saying I'm going to delete this one and this one so far, and I go to 3 to 4 for Bob, and I say, okay, add 4. Then I want to check that these are equal to each other, which, yeah, they are. So, okay, I will do this, maybe make it more interesting. And then I'm going to think about maybe some other ways to solve this, but that would be educational. So, okay. So we have another version. Here we go. So, okay, we have this other version. So you can't really see the problem, but yeah, it's over here. So we have 1 to 2. So we say, okay, so we're going to have a disjoint set for Alice and one for Bob. So at the beginning, none of them are adjoint. So the edges we have is 1, 2, 3, 4, 1, 2, 3, 4. Okay, so we go through. So we go 1, 2. And we say 1, 2, both of them can be. So I'm going to form this into a disjoint set and form this into a disjoint set. For the edge, that is 3, 1, 2. Then I have another edge, and this edge is between 2 and 3, and both of them can traverse it is type 3. So I'm going to add 3s into this set for both of them. Oops, I did not mean to include the 4. I'm kind of showing this weird. I guess to really make this, okay, let's do this differently. Let's just say, okay, so the point that I'm at right now is I have this blob here, and I have this blob here, and I have 1, 2, 3, and 1, 2, 3. And we go to the next edge. The next edge is 1 to 4 for, I think, only Alice. We have 4 here. The next one is for Bob. So I had 4 here, and I get these are equal. So cool, they can both traverse all the edges. Also, the size has to be equal to n. That is the size of both of them that be equal to n. So we're good to go. Okay, we go to our last example. So for our last example, how it's going to work is we're going to have 2 to 3. So both of them are going to be able to travel from 2 to 3. And then we have for Alice, she can travel from 1 to 2. So I say, okay, well, 1 to 2. Well, 2 is already in this set, so I'll just add 1 to this connected. So she can travel between 1, 2, and 3 because they're all connected together in her disjoint set. And for Bob, he's going to be able to travel to 4. And so this is it. So the problem here is that the size of these is not equal to 4. So this is actually going to return -1. Okay, so yeah, so I guess this algorithm will work. Um, so let's see. So yeah, I'm just gonna show my code for this. So in here is basically gonna represent the length of the array for DSU, um, the number of vertices or nodes, whatever I want to, I guess whatever doesn't matter. This since I have time, I'm just gonna actually note it that args is in, and that's an int, and the number of nodes or vertices in the graph. Okay, and then we're gonna just put this. So then I'm gonna put down here. I'm gonna put self dot parents. So initialize my parents to be a list of range n plus one. And why do I do n plus one is because everything's one index. So this is one of my notes here actually. So n plus one, because using one index for the node values. So node values are from 1 to n. So I'm create array that goes from 0, 1 to n. Yeah, and that's how you can do that. And I do self dot size equals well, they're all going to be 1 at the beginning. Cool, and then I need my definition fine. So for fine, I'm going to say, well, if x does not equal to self dot parent of x, we're going to continue iterating through because we haven't found the thing. And we're going to say self dot pair of x equal to self dot find self dot pair of x. And then I return self dot pair of x. So basically what this is going to do is going to basically this is going to provide path optimization. And you know, like why would I want to do path optimization? Well, because it does improve the time complexity. I'm not going to go analyze that too much right now. It would take too long, but yeah, this is definitely going to help with time complexity issues, and this is the cleanest code I have found for this so far. And the cool thing about it is that really every single node and every single node that's going to be put into my into one component will have the same parent, the path between these, or whenever I search one, I'm going to attach each node along its path as I traverse up to the parent. I'm going to attach all of them to the parent so that we don't have a long linked up list that's all connected to the parent, and then you know, so they're all going to be like closer. So it's like I don't know. That's very poor explanation for right now, but yeah. For union, I want to find the parents for them. So I guess I should make it more explicit and do like self-define x, yp find y, and then if xp does not equal yp, we're going to do this, otherwise we're going to turn false. That is, well, actually, otherwise we're going to turn true. So I'm thinking returns true as in we actually are going to union them. This is going to return false for this case, which is when we're going to have to union them together. This means they're already union. Or anyway, the reason for these statements is just going to be because based on if we union, we're going to want to do something different than when we don't union. I think. Anyways, it's part of my template. It has worked out quite a bit before because sometimes when you union, I want to do something different. Like I remember solving a minimum spanning tree problem with Kruskal's algorithm, and you need to do this because um, you only want to add the weight if it's not in the union. If it's already in the union, it forms a cycle. You don't want to increment the weight by the weight of that um, the those two vertices, that edge or whatever. Anyway, so I'm gonna say if self dot. So one thing I'm gonna do is I'm going to do self dot pair of xp. I'm gonna set its parent equal to. I'm gonna set yp equal to xp. So that means xp is gonna be my larger size one, and I'm gonna do self dot size of xp plus or equal to self dot size of yp, and then I don't think this is super necessary, but I just do this. I just make sure that I set this one equal to self dot size xp, just because technically that is the size of yp, right? So it makes the most sense. And then here what I'm gonna do is if self dot size of xp, if the self dot size is actually like smaller than self dot size yp, then it's kind of a different case because, or a different scenario maybe even. I'm not sure if I described that one. Wanna Yeah, so XP has got to be the larger size, so I got to swap them. And this is how I swap them, and I'm good. Move on to this. So this will be the maximum edges to remove. So I just worked my way through it. It doesn't look like I need to do any like pre-computing or pre-processing. So probably all I gotta do is go in here and for XY and the edges. Another thing about it's gonna be XYW, and nope, that's not what it's gonna be. It's gonna be type XY. I can't do that. XY in edges. Okay, so we're gonna do that, and then what I'm gonna do is I'm going to I forgot to initialize my DSU, so I'm gonna have a DSU for A, and I'm gonna have a DSU for B and K, and then what I'm gonna do is I'm gonna say if DSUA dot union, and I'm gonna try to union. I guess it depends on the type, So yeah, so let me think about this for a minute. Which one do you want to union? So if the type is 1, there's only one thing you want to union. If the type is 2, there's another thing you want to union. So I mean, yeah. So if type is equal to 1, 1 is for Alice, right? Yeah, 1 is for Alice. So if it's 1, I'm going to do a DSU A dot union XY, and then I don't know if I want to return anything here. Does it matter? I think it just matters that I'm able to union them. Oh, you know what? It does matter. Because right. Okay. So it's gonna be the size of them. Okay, so yeah. So anyway, wait a second. Huh. I just realized something. I think I did. Maybe I didn't. Okay. Anyway. Yeah. So we're gonna union them. Unless they're already in the union. And then if type is equal to 2, I don't know why I did that. Type is equal to 2, then my DSUB union XY. And I guess if type is equal, oh, you know what? I don't need to do this. All I need to do is say or type is equal to 3. So if it's equal to 3, it's still going to return true. So it's still going to union and it's going to union this one. And then the only other thing that this might be too simple. I think this won't work, but okay. Yeah, so I think that's it. So then all I have to do is say return what should be the difference? I don't know, it's not gonna be a difference in size. It's gonna more depend on if we union or not. So yeah, so it's gonna matter. So I say if type equals to 3, if DSUA dot union XY and DSUB union XY. So if both of these return true, that means they're already from a union. So I'm going to increment my answer by 1. Let me see answer. So these number nodes that I can delete. So basically, it's like if they're already in the union, I can just delete this edge. Otherwise, we have these two cases here where we're going to do this statement. We're going to say if DSU union answer plus are equal to 1. I should have done both at the same time, by the way. I don't know why I'm doing it the hard way. And plus equal to 1. This is more like an elif. This is more like an elif. This is more like an else. And then you return answer. If DSUA DSUA dot size of oh man, what would I put for size? Should I just say size of 0? I don't know. If DSU size 0, no, 0 won't make sense. 1 maybe, because there's always going to be node 1, right? Let me check. Yeah, there's always going to be 1 node. So I'm going to say if DSU size is equal to DSU beta size of 1, which is in turn equal to n. Else negative 1. Doesn't work. So it's gonna have to wait a certain length of time. It's even negative 1 for every single one, which is weird. Let's print out maybe. Let's print out DSU A dot size and DSU B dot size. See what I get here. So I get this. Interesting. So yeah, so what exactly is interesting about this is that you can see for DSUA, we can see the size 4, but the size is not working over here. So there's something going on fishy. Let me see what's going on. So, which one was it? It was DSUB that's messing up. Yeah, so DSUB is doing something weird. So what I could do is I could print out dsub.size x and dsub.size y. Huh? So weird. Uh-huh. Huh? It didn't work. I'm trying to talk, but it's hard. My voice is tired. Yeah, so 1, 2. Answer is 1. Um, oh, I know why. It's because you put the Alice, Bob, you put 1, 2, and then you put Bob 1, 2, and then you have this both one. You're like, okay, delete this. Yeah, so basically, I think you do need to sort these. Okay, I wasn't sure if I just needed pre-computing. So the time complexity isn't gonna be that bad though, so I'll do it. So let's think here. So I want to do edges dot sort key equal lambda, and these are like uh, e, and then we're gonna do in descending order, so we'll do e of 2. Whoops. This is actually gonna be 0. Interesting. So yeah, so this time complexity here to store is going to be whatever the length of edges is, which is the min between 10 to the 5th and n could be 10 to the 5th, or this form equation. So yeah, it could be up to n. So it could be n log n. And then when you do this type edges, this is what, like n time complexity. I think these are considered constant time complexity amortized. If I recall, I'll double check. I guess the time complexity of a union is O of 1, but I guess fine is log n, which, so at worst this is n log n, which we already have n log n, so should be good. Yeah, so it's n log n solution. I think that's it. So I think I forgot to talk while I was solving it, but my voice is like really bad now. So yeah, I think this template I'm gonna go with. I like this template for DSU. And then this is just the algorithm design for to solve this specific problem.